Okay, so we're gonna do our first circuit. It's almost, maybe you could call it a circuit, but first the comparator, which is an input-output relationship for the op-amp. If you never hook up the output to the input, what happens is that it's going on its inside loop, inside open loop, which is dependent on the gain, which is A. And for here, I'm gonna think this gain is, for example, 1,000,000 or 100K. And I am interested in plotting the input, which is this VD, and I am thinking VD equals the plus minus the minus, the difference in voltage, versus the output voltage. So what happens is if it were zero, there would be no zero, but it's almost, actually, that almost never happens. So as soon as this difference is a little bit, let's say 1 microvolt, my op-amp multiplies that 1 microvolt by 1,000,000. So 1 microvolt, which is 10 to the minus 6, times 10 to the 6 gives me 1 volt. So for this 1 microvolt here, I get, of course 1 microvolt's here, I get 1 volt output. Same thing's true as if the difference was minus 1 microvolt. Minus 1 microvolt times 1,000,000 is minus 1 volt. So this kind of tells me I have a linear relationship around zero, around this very small, the difference very small between the plus and the minus. However, at some point, the output reaches VCC. So imagine that I was giving it a battery of plus 10 volts and minus 10 volts. That's my battery on the op-amp. This circuit cannot spit out more than 10 volts, neither less than minus 10. So this waveform here is bounded by the rails. It's very important that you recognize that the output of the op-amp is never going to go beyond my VCC, neither below my minus VCC. And we're going to do an example next.